Hello, welcome, and thank you for joining us on this very latest Prism Sound Wednesday webinar, where today's topic for discussion is going to be related to measuring the audio performance of Bluetooth devices. So our title is How Does Your Bluetooth Audio Device Perform? And today's session will comprise some PowerPoint slides where we're going to be giving you an overview of the technologies involved and some background theory. We'll also be making some live audio measurements on some real-world Bluetooth devices to give you an understanding of the practical side of making measurements on your Bluetooth audio systems. So a quick introduction then before we lay some background theory. Today's presentation is going to be delivered by two presenters. Firstly myself, my name is Simon Woolard. I'm an applications engineer here at Prism Sound headquarters in the UK, and I work closely with our clients in the field of audio test and measurement, helping them to solve their audio measurement problems. I'm joined today by Howard Farrer, a senior applications engineer with Cambridge Silicon Radio, and CSR, for those of you that don't know, are a leading supplier and developer of Bluetooth audio and in fact in Bluetooth chipsets in general. So we'll take you through a bit of background and then we'll give you an agenda for the audio measurements that we're going to cover today. So let's first of all look at a typical Bluetooth audio system. And a Bluetooth audio system comprises two ends communicating to one another over a radio link. And at one end of the system you may have one of these types of devices, so perhaps a smartphone or a laptop, perhaps some kind of tablet, or perhaps your Bluetooth source is just a USB dongle that you connect to your computer device. Now at the other end of the link we may have one of a number of possible types of audio device, and the ubiquitous familiar looking Bluetooth audio devices that I'm sure you're all familiar with are all running what we call the hands-free profile, which is a profile specifically for telephony communications, so a bidirectional stream. And the kinds of devices you might see are these kind of things. This particular device is the headset development kit from Cambridge Silicon Radio. You might also have a Bluetooth audio system built into your in-car entertainment system to handle hands-free telephony whilst you are driving. So this is I suppose the classical Bluetooth audio system that is probably the most common type of Bluetooth device on the market at the moment. But there is another category of audio devices that is growing rapidly, and these devices use what we call the Advanced Audio Distribution Profile. And this is a high performance, wide bandwidth stereo audio streaming profile, and it's used in a number of devices that are already on the market, and that number is growing on an almost daily basis. So what kind of devices are we talking about? Well, here is one example. This is a wireless portable Bluetooth loudspeaker. So this is an active loudspeaker that allows you to stream audio content from, for example, your music collection on iTunes, etc. We have another example here. This is a pair of wireless headphones using Bluetooth, and this allows you to stream music either from your iPod, your iPad, or perhaps your PC where your music library is stored. And then finally, this is an example of a new wave of very high-end audio products that also incorporate Bluetooth audio connectivity. And this device is a very high-end hi-fi D2A converter and preamp with an inbuilt Bluetooth wireless receiver. So this gives you an idea of the kind of products that we're talking about when we make the measurements that we're going to be looking at today. And now I'm going to ask Howard Farrer from Cambridge Silicon Radio to talk us through the Cambridge Silicon Radio hardware platform that we're going to be using for the purpose of today's practical demonstrations. So I would be grateful, Howard, if you could please take us through a description of the Cambridge Silicon Radio platform, which will lead us into our agenda for what we're going to measure today.
Hi, thanks, Simon. CSR produces quite a few different Bluetooth devices, ranging from ROM parts to which are used in the mono headset, which Simon mentioned earlier, to BC5 Multimedia, which is our flagship product at the moment, which is a complete system on a chip which is user programmable. In the BC5MM, we've got an antenna input which goes into the 2.4 gigahertz radio and the baseband DSP, which produces the Bluetooth packets, which are then passed on to the microcontroller. The microcontroller does all the protocol stack that supports things like the AVRCP, and RFCOM, which is the serial interface over Bluetooth. We then got RAM for the user applications as well as the product firmware, and then we've also got a rather high power or high performance, I should say, low power DSP, which is 24-bit, 64 megahertz, with quite a bit of memory to it. I think it's about 48k words of memory in total. And then we've got some I/O where we can talk directly to external flash chip, which stores the user programs. We've got the UART, which I mentioned earlier, the PIO, where we can directly control I/O pins to flash LEDs or even bit bashed interfaces or any other interfaces we might want to create. We've also got analog audio input and output. We've got on-chip microphone amplifiers, so we can interface directly to microphones, and we've also got an on-chip power amplifier, so a headset device will only need this chip and microphone and speaker plus a few passives. Then we've also got digital audio I/O, so we've got I2S, PCM, MSB First, and also SPDIF I/O. And we're going to be using a couple of tests today which are going to use both the analog and digital interfaces. And then finally we've got an SPI interface which we use primarily for debugging. So got these boards which have got the BC5MM on. The BC5 is in the small white rectangle you can see there on the left hand side of the board. To give an idea of scale, the little white rectangle is 20 millimeters by 25 millimeters, and that contains all the devices you need to implement a full Bluetooth solution. So the device on the left we're going to be using as the audio adapter, or effectively the Bluetooth transmitter in this situation. In some of the tests we're going to be using it as a USB sound card, taking digital audio directly from PC, and in other tests we're going to be using the analog input. That's going to be connected via Bluetooth to the second board, which is going to be the headset application, which you see typically in a telephony headset or a headphone or loudspeaker. Again, we're going to be using a mixture of the analog or the digital I/O.
Okay, thank you for the overview there, Howard. So now we have a good understanding of not only the kind of real-world devices that might be using a Bluetooth chipset such as the one we've just seen, but we also have an understanding of the kind of functionality that the Bluetooth chipset itself may offer. And that gives us a bit of an idea about the kind of audio functionality and the audio subsystems in our Bluetooth device, which then leads on to the kind of measurements that we might want to make in order to verify the performance of that Bluetooth audio system. So let's now then take a look at today's audio analysis agenda, which is designed to give us a snapshot of some of the things that we would want to do to measure our Bluetooth audio device. So first of all, we're going to take a look at the Bluetooth radio link itself, and we're going to set up a test for establishing whether the Bluetooth link is operating free from any problems with dropouts, glitches, packet loss, all those kind of things that you might want to check early on when A, establishing that the link works, and B, establishing over what range your Bluetooth device is operating free from any dropouts, lost packets, etc. Howard has already illustrated to us that the Cambridge Silicon Radio chipset incorporates digital to analog and analog to digital converters. Within the DSP, everything is handled digitally, but we have some real-world connectors that allow us to connect analog microphones as inputs, headphone or loudspeaker transducers as outputs, and they will be operating in the analog domain, so we therefore need converters to convert those analog signals to and from the digital domain. So we'll take a look at measuring converters. We'll move on to take a look at some of the codecs that can potentially run on a Bluetooth audio platform, and these codecs are designed to packetize up the audio content and to compress it down to a size that can be distributed over a Bluetooth radio link. And there are a range of codecs that could be used. They have varying degrees of performance in terms of how good they sound, how well they measure in an audio context, and we're going to look at how we go about quantifying just how well the codec itself is performing. You may well have some kind of signal processing, whether it's some basic band limiting in terms of equalization, or perhaps more sophisticated equalization to equalize out any resonances in the loudspeaker. There may be dynamics processing as well, perhaps to protect some of your components, the amplifiers, the transducers from being overdriven, etc. So we'll look at some measurements there. We'll then move on to look at the power amplifiers, and as Howard identified, there is a headphone amplifier built into the Bluetooth solution from Cambridge Silicon Radio, and we'll take a look at a couple of measurements that you might want to make on a power amplifier, whether that be a headphone amplifier or indeed an amplifier designed to drive a lower impedance, higher power load like an active loudspeaker, for example. And then finally we're going to take a look at measuring the electroacoustic components of our Bluetooth system, whether that be the microphone for a headset or whether that's the earpieces or transducers for a loudspeaker or headphone. So that's our agenda. We have a lot to cover, and that means that we're only really going to be scratching the surface of each of these issues, but it will certainly give you an idea of where to go about starting to analyse the various subsystems within your Bluetooth audio device, and we can give you some references to some further reading, further viewing that will drill down into more detail into some of these areas in other webinars that we have delivered in the past. So firstly then, let's take a look at checking the Bluetooth radio link for audio dropouts. And what I want to do before I go through this section is just to ask you for some feedback. So I'm going to launch a survey now, and this survey will appear on your screens provided you are a PC user. What I'd like you to do is to read all of the possible options in the survey that I've just launched here, and tell me which methods you think would be appropriate for testing a Bluetooth radio link, specifically looking for audio dropouts and glitches. There are a number of possibilities, and I would like you to identify all of those that you think may be useful in respect of looking for audio dropouts, glitches over a Bluetooth radio link. So I would be grateful if you could fill those in. The survey is anonymous. We shan't be embarrassing anybody if any of you have put an answer in that we don't think is the right answer. Please just complete it as honestly as you can, and we'll then take a look at the results. So I'll bring that survey to a close now, and let's take a look at the results. Okay, so we have a good number of responses here, and there is a good spread of answers as well. And there are quite a few options here. We could listen to the signal, we could inspect it on an oscilloscope, we could measure the signal amplitude, the distortion amplitude, we could look at the FFT, we could run a digital transparency test. Actually, in fairness to you all, I've been a little bit cruel today, and all of the methods that I have identified as possibilities for checking the Bluetooth radio link for dropouts really aren't actually terribly satisfactory. They might be helpful in some situations, but they're not a robust, guaranteed way of picking up every possible glitch dropout. And I'm going to explain that in some detail as we go through the demonstration. The first thing I want to say is that whilst the digital transparency test would in principle be a very robust and reliable method for picking up even a least significant bit in error in a digital system, unfortunately in a Bluetooth radio link we are using some form of lossy compression in our codec, so there is no way of checking all of the bits at the output and comparing them against all the bits at the input, because there will be changes by virtue of the lossy codec. So that is that method written off, unfortunately, from the outset. The remainder of these issues I will come back to when we jump into the live demonstration and explain the method that you really ought to use if you want to ensure that you are guaranteeing picking up every possible glitch or dropout. So, in order to illustrate that then, here is the measurement setup that I will be using. And I am using the Prism Sound D-Scope Series 3 audio tester measurement platform. This is a general purpose platform for a wide range of measurements, from analog electronics to digital electronics, through to electroacoustic measurements. And in particular, we're using this system today because of its ability to directly address Bluetooth audio devices and to allow us to make a closed loop measurement of our Bluetooth device without having to invoke any external processes in audio editing workstations, in signal generating software. It can all be done in a closed loop with this particular system. So the D-Scope software that's running on my PC at the moment can address our CSR 1645 boards directly, and we can dynamically change the signal generator levels, frequencies, etc. And I'll show you how to do that in just a second. So this is the source end. We're going to be transmitting a stereo audio stream to a second Bluetooth board, this time running a headset profile, and I'm going to take the analog outputs from that particular board in order to make my measurements. So here is the tester measurement setup. This is what's on the bench in front of Howard and myself at the moment, and we'll be using a number of these components in this system as we go through the measurements here today. So I'm going to jump into the D-Scope tester measurement system here, and I'm just showing you one particular test file at the moment that I've set up for this dropout test. Now here is the sound card output panel that allows me to address any Windows audio device that is connected to my computer that I'm currently running the D-Scope software on. So there are a number of devices connected to my host PC here, including my onboard Bluetooth audio chipset on the laptop that I'm using today. But what I'm going to do is route my audio signal directly to this CSR Bluetooth dongle. So this is my USB dongle connected to my computer, and as soon as I do that, we will register a signal at this signal analyzer, and we'll also be able to hear from the monitor output of my analyzer that we have a signal present. So I have now assigned my output to the CSR Bluetooth dongle, and here we are generating our sinusoidal signal that you see on the trace window in front of you. So I can dynamically adjust the signal amplitude, I can change the signal frequency, I can even change the waveform. This is all happening on the fly in real time, allowing me to test my Bluetooth system from end to end in a closed loop. And this is important. This is something we're going to be using quite extensively in today's demonstrations. So on to the link test then. I'm just going to start to explain now why some of the methods that we identified in the survey are unsatisfactory from the point of view of checking our Bluetooth radio link for dropouts. So, at our signal analyzer now, we're registering this sine wave. It all looks okay. Let's take a listen. That all sounds okay to me. I can hear a continuous sine wave. You may be forgiven for thinking there's nothing wrong with this signal right now, but watch what happens if I listen to, instead of the wideband signal, I'm going to apply a notch filter at the tone frequency, and we're just going to listen to the residual noise and distortion instead. And you can hear there that there is a series of ticks. They're low-level ticks, low-level glitches that are ordinarily masked by the signal. So we've just proven that it's no good just listening to the signal, because there may be low-level artifacts there that are indicative of bigger problems to come. And of course we can't see any problems in the sine wave here. Let's take a look at some audio measurements then. Here in the top panel I have a measurement with some fairly tight limits applied, analysing the RMS signal amplitude, currently showing us 83.5 millivolts. That's okay, the reading is within limits, there's no breaches going on, and everything looks okay. As with this THD plus N measurement, we're measuring approximately minus 60 dB here, give or take. And this measurement is also within limits and showing us that everything seems okay. But watch what happens when I bring up this measurement here. And this measurement comes from this continuous time detector here, and I have set up a THD plus N measurement, but importantly I'm using a true peak measurement. So this is an oversampled interpolated measurement of the residual noise and distortion, and we now see some flashes, some limit breaches in this reading panel on the left hand side here, and this has identified correctly that we have some glitches in our audio signal, and in fact they are being recorded to a file, so that even if these happen only very infrequently, or perhaps when you're not sitting monitoring the instrument, these are all being recorded and logged into a file over an indefinite time period, so we can really test the robustness over whatever time period we're interested in measuring. So let me just quickly then explain what is happening here. We've looked at the time domain trace here in green, and we've seen really nothing wrong. Let's take a look at the residual distortion trace. So this is the time domain waveform of the THD plus N products. And if I just measure a relatively large FFT capture here, let's take a look, if we zoom out, at what we see. Now the sine wave looks fine, the noise and distortion trace looks fine. But what's that? Let's zoom in here and take a look. We can see that there is a significant glitch in the residual noise and distortion waveform here, and if I zoom right in, we can see that even on this scale it's very hard to see anything wrong with the audio signal itself. If I just show you the sine wave here, what I have done here is that I have actually deliberately engineered a one sample deviation of 2 dB in this waveform that I'm playing out of the D-Scope system here over the Bluetooth radio link. And just this tiny little deviation in the waveform here has been enough to cause a huge and measurable deviation in the peak THD plus noise residual. And so hopefully what I've done here is illustrated to you that this is a very powerful method for picking up even the smallest deviations, glitches, dropouts in your Bluetooth audio system. And yes, you could argue that in the real world you may lose an entire packet, which would be a significantly bigger glitch than the one that we're engineering here on the bench. But this shows you that this particular method is extremely robust and reliable and will pick up even the smallest glitches with absolute certainty. So that being said, let's move on to the next topic now, and we're going to take a look at measuring D to A or A to D converters. And as I explained earlier, we have some analog components, so microphones, amplifiers, loudspeakers, that require conversion to and from the digital domain inside the Bluetooth audio device. So I'm going to make a measurement of a D to A converter, which would be typically upstream of your power amplifier that's driving your headset earpiece or your loudspeaker transducer. In order to do that, I'm using once again the D-Scope tester measurement platform, and this time I'm going to isolate just the D to A converter. So we're not going to make the measurement over a wireless link, we're just going to go straight into the D to A converter digitally and come out in the analog domain, so we can isolate that particular device, which is likely to be one of the highest performance devices in the Bluetooth system. Therefore we need to measure it directly in order to quantify its performance accurately. So here I introduce another device from the Prism Sound product range, which is a converter that converts the native AES digital I/O of the D-Scope hardware to and from serial data formats. And the CSR Bluecore 5 multimedia chipset can support a number of serial digital audio formats, including I2S into IC sound. So in this example we're going to generate an I2S format digital audio input to the D to A converter, and we're going to measure the analog output. Therefore we'll be quantifying the performance of the D to A converter. So I'll step back to my tester measurement system here, the D-Scope 3 system, and let's set up our D to A converter measurement. Now I just need to manually change a couple of connections here in my setup, which is now done. I've got a little note to self here to do that. And what I need to do now is configure the VSIO adapter, in particular configure its clock and data formats to match that of the D to A converter chip that I want to measure. And I have taken this graphical snapshot here from the datasheet of my digital to analog converter, and this shows me the clock and data format for the word clock at the top, the bit clock in the middle, and the audio data format at the bottom. So what I need to do is ensure that the clock and data format in my test and measurement system matches that which is expected by my D2A converter chip. So firstly, let's look at the word clock here. Well, this is actually firing in such a way that the left channel data, which comes first in the stream, is actually happening when there is a downward clock pulse, so a positive to negative clock transition. So that means that I need to invert the word clock here in the test and measurement system. So I hit this button here, and this word clock is now taking on that inverted form. We also see that the word clock fires one bit clock cycle earlier than the most significant bit of the audio data. So I also need to select this early option here. And we can see that the bit clock itself is also inverted. So the most significant bit here starts on a negative clock transition. So if I invert the bit clock here, we now see that the timing diagram in the VSIO adapter in the test and measurement platform matches the timing diagram here on the datasheet, apart from the audio data format. And we see that the audio data is arranged with the most significant bit first. Currently we have least significant bit first in the test system, so if I uncheck this, now we have a perfect match between the clock and data formats of the test system and the device under test. So I'll just enable the serial digital audio data generation here, and my D2A converter has now come to life, and we can see here that we have a green sinusoidal waveform and a corresponding red FFT spectrum showing us the output of this D2A converter. There are many measurements you might want to make on your D2A converter to quantify its performance, and generally the starting point is the manufacturer's datasheet for that part to ensure that you have implemented the reference design or your own interpretation of the reference design without impacting on the performance of that component. Now, I only have time to show you one measurement here today, and I'm going to make a linearity measurement. So I'm going to measure the input amplitude versus the output amplitude. And here is the manufacturer's quoted performance for the linearity response. And again, this would be just one of many graphs from the manufacturer, and you can set up the D-Scope Series 3 test system to perform all of those various different measurements and to ensure that you do have the same performance as the datasheet specifies. So what I'm going to do to measure this amplitude response is to set up what we call a sweep. So we're measuring one of a very large number of possible variables. In this case, we're just going to measure the output amplitude of the D2A converter on channel A and on channel B. We can have up to 4 results, but I'm just going to measure 2 for now. So we're going to measure the output amplitude of the D2A, and we're going to vary the generator amplitude of the D-Scope digital output. Now what I'm going to do to set this up in the most efficient way is that I'm going to define a custom sweep here. And ordinarily you could choose between a linear or logarithmic distribution of data points, but I want to have an arbitrary distribution here. The reason being that I want to focus my attention on the low amplitude end of this trace, where we know that this device is going to start to become non-linear. At relatively high amplitudes we expect to have a nice straight line, and therefore we don't necessarily want to waste too much time populating this upper part of the trace with too many data points. So I have a custom distribution of amplitudes here, so starting with 30 dB increments between sweep data points, then we tighten up to 20 before the last few data points here are at 5 dB intervals, and you can set these up to be whatever you like. This is totally arbitrary. So that's my sweep set up, and all I have to do now is hit the go button, and the sweep is now executing live on the screen as I speak. So we now see the sweep measurements on the screen, and we can see that these results correlate very closely with the manufacturer's datasheet. So we can now satisfy ourselves that, at least from the point of view of amplitude linearity, we have done nothing in our design to compromise the performance of this particular chipset. Now, of course, you would now move on to measure a number of other parameters, but time does not permit, so I'm going to move on to the next section of today's presentation. So the next part of today's presentation, we're going to talk about quantifying the performance of the codec itself. So this is the encoder and decoder used to bundle up our audio data before it's transmitted over the Bluetooth radio link. And the idea here is to reduce the data rate so that we're not consuming so much bandwidth. We therefore have a more reliable, robust radio link that works over a longer range. And in order to talk us through the kind of codecs that are available for use in Bluetooth systems and how you might go about quantifying their relative performance, I'm once again going to hand over to Howard Farrer from Cambridge Silicon Radio, who will talk us through this part of the presentation. So once again, Howard, it's over to you.
Thank you, Simon. In Bluetooth A2DP systems, we've got a mandatory codec called SBC, or subband codec. As I said, this is a mandatory codec. There's also provision in the specification for putting other codecs, which is like what we've done with aptX or also with AAC. But SBC is a fixed rate codec which can code up to around 350 kilobits per second. As I say, this is up to 350 kilobits per second. We find some products which actually support the maximum bit rate, but we've also found products which only support up to, say, 200 kilobits per second, which has significant consequences in terms of signal quality and frequency extension. And the other problem we get is that it's a negotiated rate. So if you've got a high quality stereo headset which can do 350 kbps, then and you connect that to an MP3 player which only does 200 kbps, then the signal quality of the link will be 200. It was originally adopted in the specification primarily because it's a low power codec. It's fairly low complexity in both the encode and decode. For example, in the Kalimba DSP that we have inside the BC5MM, the codec only takes about 8 MIPS, which is an incredibly low power consumption. But the SBC codec doesn't have any certification process, and there's many different implementations out there, some good, some not so good. However, with aptX, we've got for people who don't know, aptX was developed by APT in approximately 10 or more years ago, and it's been used in the broadcast industry quite significantly. So if you've been listening to radio over FM or DAB, then there's a chance you have been listening to the aptX codec without realizing, because most of the broadcast industry uses it for transmitting between audio between the transmitters. In 2008, aptX released a Bluetooth variant of the codec, and then CSR acquired aptX in about 2010 because we liked it so much, although we still allow other people to implement the aptX codec if they want on other platforms. In fact, we have quite a number of customers supporting aptX. For example, Apple have implemented it in OS X, and also Samsung are using it in quite a lot of their new products. We find it substantially improves on the SBC performance in terms of audio quality, and a couple of measurements I'm going to show today should hopefully show how it's also demonstrably better. And one of the advantages we have is that it's a fixed bit rate, so unlike SBC, the bitrate is always a 4:1 compression ratio. We find this gives a good sound quality, but it also means you don't have the problem where you get a negotiated bitrate and the lowest common denominator wins. And finally, we have an official certification process for any products that you might see on the shelves. This means that anything that gets released, we've passed it to make sure that it's got sufficient sound quality for our purposes. So we're just going to do a couple of very quick little measurements here just to show the advantages of aptX over SBC. The way we're going to do this is we're going to use the Dscope 3 again. We're going to have two 1645 boards. One's going to be implementing a USB dongle, so we're going to be taking digital audio straight from the PC, driven by the Dscope software and using the sound card feature. And then we're going to have a Bluetooth link to the second 1645 board, where we're going to take the digital SPDIF output straight into the digital input on the Dscope. So if we just switch to the Dscope software, I've already got a trace running here, which is an active Bluetooth link running SBC. So we've got a 1 kHz sine wave with quite a few distortion components here. In fact, if I turn on the averaging, you can see there's also another distortion component which was lurking in the noise floor just there. So we find that that kind of causes problems with the sound quality of the system. So if I switch to another audio adapter which I've got running using the aptX codec, and then switch over the to another headset which is also running aptX, I take a copy of the current trace and then run the new one. This is running aptX, so you can see although we've got a slightly higher noise floor, it's we've got rid of all of those nasty high order distortion components there, which will going to be discordant and cause problems with the sound quality. So if I then switch back to the SBC decoder, because we're going to do an IMD measurement where we're going to take the same 1 kHz sine wave at minus 20 dBFS, but then we're going to modulate that with a or add a 60 Hz signal as well at a slightly higher level. So this is fairly representative of what you'd get in a music system. And you can see here we've got, if we turn on the averaging again, you've got quite a lot of distortion components coming in. We not only do we have the distortion components we had before from the 1 kHz sine wave, we've also got some quite horrible sidebands as well. So if I take a copy of that trace and then switch to, in a lovely fashionable pink, and then switch to the SBC, the aptX codec. Got a lock, and run that again. You can see here that we've got, if I change the colour there to make it a little bit more visible, the differences. No, sorry, wrong trace. You can see the blue aptX trace has got no distortion components at all. Again, we've got a very slight increase in noise floor, but you can liken this to when you add dither to any digital audio system. You get a slight increase in the signal to noise ratio, or decrease in the signal to noise ratio, but you get a vast improvement in the distortion response. So you get a better quality sound. The next test I'm going to do, if we go back to the presentation, is going to be a latency measurement. Again, we're using the Dscope 3, but this time we're using another set of boards I've got wired up using the analog outputs. This kind of helps show the fact we've got multi-mode testing here, and also means that I don't have to change lots of inputs all the time. So we've got a 1645 board with the analog input, which is then Bluetooth link across to another 1645, and we're taking the analog output of that into the Dscope Series 3. So if we just load the test, you can see what we've got here is a very brief chirp. It's only about 5 cycles of a 1 kHz sine wave, which we're outputting from, this is what's going into the first 1645 board, and then the bottom trace is what we're getting back from the Bluetooth link. Now if we run the script here, which kind of measures the signal coming back and to tell us the latency, you can see we've got about 220 milliseconds of latency here, which is not very good for any kind of real-time applications. It's like if you want AV headset or for gaming. So if we now switch this to aptX, where we've got a special low latency implementation here, we're got a latency now of 35 milliseconds, which is less than one video frame in either PAL or NTSC territories. This means that you can now use Bluetooth for audio-visual applications and gaming. So, for example, you've got a quite a big market for gestural and controllers or wireless controllers nowadays. If you've got a gaming headset, you don't want wires trailing around when you've got a wireless remote. So now you can have the wireless headset and a wireless remote control as well. So back over to Simon.
Okay, thank you very much, Howard. And that's quite a compelling demonstration there, showing you two codecs running on identical hardware. In fact, it is actually the same board that Howard was running those two different codecs on, and shows you that using the same Bluetooth link, consuming the same bandwidth, there is potentially quite a wide variation in the performance of the various codecs that you could be running on your Bluetooth system. So it's well worth understanding how you go about quantifying those differences in order to help you select the most appropriate codec for the device that you're designing. And in particular there we saw that the aptX implementation is particularly high quality when compared to the mandated subband codec. Okay, so now we will talk about signal processing. So as I said earlier, this may be equalization that you provide to the user to adjust the spectral balance of sound through the system. It may be corrective EQ to deal with anomalies in the acoustic response of the transducers or the transducers loaded in their enclosure. And you may have some dynamics processing as well. These are all the kind of things that you might want to quantify. And we're going to take a look at one of the measurements you might want to make. So once again, I will ask you for your feedback before we dive into this particular demonstration here. And I've launched another survey that those of you using Windows PCs will be able to participate in. So I'm asking you to tell me which methods you have used in the past for measuring frequency response of your audio devices. It may be that you've worked on Bluetooth devices, it may be that you've worked on other audio devices, but if you've ever measured the frequency response of any of those systems, I would be grateful if you could tell me which methods of the ones I have proposed that you may have used in the past. And that will lead us on to looking at a very specific method that's very powerful for measuring frequency response. So once again, this survey is anonymous. I'd be grateful if you'd take the time to fill in your responses for me, please. And in just a second or two, we will take a look at the results before moving on to the demonstration. So I'll bring that survey to a close now, and we can take a look at how you have all responded. Okay, so we have a wide range of responses here where at least one of you has used all of the above methods. Somebody hasn't used any of the above. That may mean that they've used some other method, or perhaps that person hasn't actually made any frequency response measurements in the past. All of these measurements are valid. I would say about the pink and the white noise method that unless you're combining that with an impulse response, you won't get a terribly clean looking frequency response. There will be variations from one data point to another that reflect the spectrum of the noise rather than variations in the frequency response of the device you're testing. So noise generally is not terribly satisfactory for measuring frequency response. You have to do a lot of averaging in your real-time analyzer or your FFT analyzer in order to get close to a clean looking result, and even then it's not that clean. Sinusoidal sweeps, well, we've just had an example measurement of a sweep where we looked at our D to A converter amplitude linearity. We can make a frequency response sweep quite easily, and that is perhaps the most common method for measuring frequency responses in electronic systems, and it's no real surprise that the largest number of respondents have said that they use a sinusoidal sweep above any other method. Impulse response methods combined with FFT processing, that's very powerful. We'll look at that later when we look at transducer measurements. But the one method that I want to dwell on more than anything is the multitone method. And it's good to see that some of you have already used multitones. I'm going to talk about a very particular type of multitone here today, and that is what we call the bin centers multitone. So before we take a look at that measurement, let's just once again explain the setup that we have here today on the bench in front of us. And we are of course once again using the D-Scope Series 3 tester measurement system. We are applying a signal over the Bluetooth radio link directly using the CSR 1645 Bluetooth transmitter dongle. And we're going to be making measurements on the analog outputs of our headset profile receiver. Okay, so let's jump into the measurement now, and let's open this test file here. Okay, so if I just go into my signal generator here, we see that we have a wide range of generator functions available to us, including totally arbitrary waveforms. And using this very flexible signal generator, we can define arbitrary multitones which have applications beyond just measuring frequency response. But today I'm just going to keep it relatively simple and talk about the bin centers multitone. And this is perhaps the most extreme type of multitone you're likely to encounter. And this contains, in this particular case, I've chosen 8,000 samples in my bin centers multitone, which actually means there are 4,000 sinusoidal tones in the real frequency axis. So this is a very tightly packed, very densely populated multitone playing over 4,000 discrete sinusoidal tones all at the same time. I'm going to analyze this using an FFT measurement where the number of data points in my FFT exactly corresponds to the number of samples in my generator sequence. And that gives us a rather interesting result. On the screen at the moment, the white trace is showing you a previously measured result that I made before the session started, where I used a very large FFT size, and in doing so I've been able to expose these discrete tone components in our bin centers multitone. Let's just take a quick listen to it using the D-Scope monitor output. So it sounds almost noise-like. There are so many sinusoids in this signal that it sounds almost like noise. Now let's go to my live measurement where I have set up an analysis using the same number of tones as I have points in my FFT here. And what we see is a very interesting result. My white FFT now shows me a flat line, which is currently a measurement of the EQ of the system that I have on the bench in front of me. Now I have also wired into the circuit an EQ device that allows me to make real-time changes to my equalization settings, and we'll now see the power of this particular method above the other methods that we've just talked about. And the great thing about this is that we can make real-time changes to our EQ settings, as I am doing now, and we see those updates in almost real time. This is updating at about 3 or 4 times a second, so every second we get 3 complete measurements of a frequency response with, in this case, in excess of 4,000 data points in this frequency response measurement. So this is extremely powerful, in particular if you have a system that has variable EQ settings. Perhaps they're user adjustable, perhaps they're dynamic EQs that adapt to the acoustic conditions in which the system's being operated. This allows you to make close to real-time measurements of a very large number of DSP settings in very little time at all. Particularly for those of you that have used sweeps, this is particularly fast compared to the traditional sinusoidal swept method. Okay, so I hope that's clear, and you now appreciate the power of that particular method. But I'm now going to move on and talk about the next topic here today. So we're going to look at a couple of examples of the things you might want to do when measuring the output of a power amplifier. And in the Bluetooth audio context, this is the amplifier that's either driving your earpiece in your headset or in your headphones, or perhaps a bigger amplifier driving some larger transducers in your active loudspeaker that incorporates Bluetooth wireless functionality. So let's take a look at the setup. Little change from the last one, with the exception that now at the receiving end of the Bluetooth wireless link, I am taking the headphone amplifier outputs and I am making sure that I'm driving into a representative resistance, in this case a 32 ohm load, to emulate the type of load that the headphone transducers will present to the headphone amplifier. For a loudspeaker load, for a higher power amplifier, you might be typically talking a 4 ohm or an 8 ohm load. In headphones, we typically deal with higher impedances, and 32 ohms is a common resistive load to drive into for measurement purposes. Okay, so let's go back to the D-Scope system and load my power output measurement configuration file here. And once again, as I explained in my diagram, I'm using the real-time addressing functionality where we can route our signal directly to our Bluetooth USB dongle, and we're just making a couple of reconnections here so we can make this measurement. Once we have done that, I will now select the Bluetooth USB dongle as my output device, and we can now see the signal that is coming back at the signal analyzer. So this is at the receiving end of the wireless link and is the output from the headphone amplifier. Now, in order to ascertain the output power of my power amplifier, and this is perhaps one of the first things you might want to do when you're analysing your power amplifier, what I need to do is adjust the input level to this system and determine the point at which the output harmonic distortion reaches 1%. That is the usual definition. Some people use 10%, but it matters not to the Dscope system. You can use whichever is your preference in whatever standard you're working to. So what I could do, I could go in here and manually increase the output that I'm driving over the wireless link. Let's go up a bit more. Let's go to -1. Oh, and I'm in clipping now. I've reached 2.1% distortion, which according to my 1% definition is over target. So let's drop this level back down again. Let's go down a couple of dB. Oh, we're now below target. So this is actually quite a tricky process, and what we normally recommend is that you use what we call a regulation routine in order to automatically find the onset of clipping, the point where the distortion reaches 1%. So I've set up a regulation here where we are, in this case, choosing the continuous time detector, our real-time distortion analyzer, and we are seeking out a target value of 1% THD plus N. And in order to seek out this particular target, what I'm doing is I'm varying the generator amplitude, and in doing so we can look for the point at which the output level, or rather the output distortion of our headphone amplifier reaches 1%. So I'm ready to run this test now. You'll see that I have some red lights here showing that we're outside the limits at the moment. These readings will tell you OK once we're in limit, and independently of that, this regulation routine will also actually automatically find that point for us. So let's go, let's regulate. And what we'll see now is that we'll get some live updates to the signal amplitude on the screen, and we've already now found the clipping point. So the regulation has reported success. Our measurement here, just to confirm that, shows us that we have reached our target value of 1%, and that occurs at the point where the power amplifier output has reached 214 millivolts, or just below. And because we're measuring a power amplifier here, we now want to quantify that in terms of electrical power. So Dscope has interpreted this as 1.4 milliwatts, accounting for the 32 ohm load that this voltage is being driven across. One thing you might want to do is to check whether your power amplifier has been correctly designed in terms of the thermal relief, and you might want to monitor this over a period of time. So once again, we're going to use this very powerful set of tools in the Dscope that allows us to monitor a wide range of results over time. So here I'm monitoring the THD plus noise and also the RMS amplitude, and in doing so I'm able to determine whether or not my power amplifier can sustain this output level over a period of time that I may define. And typically you might test for an hour or for 24 hours. You might want to run it for longer than that if you suspect an intermittent problem. So let's now emulate a case where my amplifier is now overheating, the thermal protection circuitry starts to activate, and it reduces the gain of the amplifier to reduce the dissipation and therefore reduce the temperature at the heat sinks. So I can turn the level down on my Bluetooth device here, and I have now emulated a fault condition where my amplifier level has started to drop. Now this may have happened while you have your back turned, whilst you're out of the lab, and it may be that the temperature has reduced and the thermal protection circuitry has recovered whilst you're not looking, and we are now back to a condition where the amplitude looks okay, as does the distortion. And that is where the power of this log file comes in, and we've now got a complete record complete with time and date stamps and information about the event here, telling us that the amplitude readings breached their limits, and it gives us actually a readout of what those values were when they breached. So this is a very good long-term stability test for looking at the kind of intermittent problems that you might have when designing or integrating a power amplifier into your Bluetooth audio system. Once again, there's a lot more we could talk about in terms of amplifier measurements, but we're going to move the discussion on to the final stage of your Bluetooth audio system, which in many cases incorporates some kind of electroacoustic transducers, whether they're microphones for headsets or earpieces or loudspeaker transducers in a headphone or wireless loudspeaker Bluetooth scenario. So let's look at this test and measurement setup, and once again I'm using the Dscope analyzer platform. In this case I'm introducing another new component, and this is an ear and cheek simulator from a Danish company called Grass, who specialises in electroacoustic measurement fixtures. And I'm going to connect the analog output from Dscope to the analog input of the power amplifier, so we're just going to analyse the headset and nothing else. And what we'll do is we'll take an output signal from the microphone power supply into the Dscope analyzer, and we'll be able to measure the performance of this headset. So why an ear and cheek simulator then? Well, the ear and cheek simulator is designed to do a couple of things. Firstly, it models the human pinna, the outer ear. So this pinna that you see in the ear and cheek simulator is representative of the dimensions, the geometry, and also the mechanical stiffness and damping of a real human ear. Inside the fixture here we also have what we call an IEC 711 coupler, and this is designed to closely emulate the acoustic impedance of the ear canal, the inner ear. So in other words, this complete test fixture is designed to give us a close working model of a real human ear, and this means that we can make repeatable measurements without needing to have a human subject to subject to our acoustic measurements. And that's both impractical in terms of the man hours involved in your human subject, and it's also potentially dangerous if you're talking about inserting probe microphones into a human ear. So let's switch over to the Dscope test system and launch my final measurement for today. So this is just launching. I just need to make a couple of connections to my system under test, which is all ready to go now, and I will make my measurement and then explain what I have done. So let's just hit this run test button, and the test is now executing, and we have a number of results now appeared on your screen. So let's talk through these in turn. What you perhaps didn't hear there is that in my signal generator I have what we call a swept sine, or a chirp stimulus defined, and this is a logarithmically swept chirp in this particular example. This is effectively a wideband stimulus. It sweeps over a wide range of frequencies and gives us a broadband stimulus, which allows us to mathematically calculate the impulse response of the system we're testing. Having derived the impulse response, we can then apply this time domain window function, which is designed to allow us to remove any reflections. So this is particularly useful for electroacoustic measurements of headphones, of loudspeakers, where you're working in a non-anechoic environment. So once we've applied this window function, we then pass the output to the FFT engine, and that gives us this red frequency response here that you see on your screens at the moment. Now, one thing that's unique about this logarithmically swept chirp that I've just shown you is that in addition to this fundamental impulse response here that gives us our frequency response, if I just zoom out and expand the y-axis scale here, you can see that we also have a series of discrete impulses at the end of this impulse response buffer here, and these correspond to the harmonic distortion products of the device that we've just tested. So in addition to being able to measure the frequency response, or fundamental, we can also measure things like the second harmonic distortion product, the third harmonic, the THD. In fact, we can have up to the eighth harmonic, or even further if we wanted to. But in actual fact, in electroacoustic measurements, we're usually only concerned with the second and third harmonic because they tend to dominate the total harmonic distortion of these types of devices. So we have our frequency response measurement, we now have our distortion measurement, and this is our headset quantified. Well, those of you who perhaps haven't measured a headset before, maybe more used to measuring loudspeakers, this frequency response looks a little bit unusual. We've got quite a large resonance here over the 2 kHz to 6 kHz region. This in fact is down to the ear canal resonance in the ear and cheek simulator fixture that we're using here in the demonstration. So this is what actually happens in your ear, but you are psychoacoustically adjusted to this, and this doesn't sound like a huge great resonance that you might expect it to sound like if this was actually originating from a loudspeaker. So you might actually want to take that acoustic resonance out of the measurement and just simply quantify the performance of the headset itself. And we can do that by selecting a pre-weighting filter here that has been designed to compensate for that ear canal resonance in the ear and cheek simulator. So if I now take a copy of that original measurement, rerun the test, we now see a frequency response measurement in red that has been corrected for that ear canal resonance, and we now see a frequency response that will make you feel much more comfortable if you're used to looking at, for example, loudspeaker measurements. This is actually the inherent performance of the headset itself, excluding the ear canal resonance. Okay, so that brings to a close the formal demonstrations here today. What I'd just like to do before handing over to you for the Q&A session is to give Howard firstly an opportunity to summarise what he's discussed today. I'll then quickly round up what I have discussed before, as I say, then moving on to the Q&A session. So I will hand you back to Howard to just give us a brief summary of what he has presented on CSR's behalf today.
Hi, thank you, Simon. Yeah, we saw earlier that we were using the BC5MM on a 1645 board, as you can see down here. This is a multifunctional platform where it's user programmable, both in terms of the DSP and in the host functionality. You can implement various different platforms on it for voice, stereo audio. You can either pass data over it or control, as I said earlier about AVRCP, where you have a stereo headset which has transport controls on it, and those go back over Bluetooth, because it's a bi-directional link, back to your MP3 player to control the audio, whether it be the volume or track select. We've also demonstrated the low latencies that we can get using aptX low latency implementation, and we've also demonstrated how you can actually get a high quality link, where most people think that Bluetooth is low quality, high latency. Well, we've shown here that it can be both, and use the various features of a D-Scope to demonstrate that.
Okay, thank you then, Howard, for your quick recap there, and I will just do the same. So to summarise what I have talked about today, well, I just want to go back firstly to the first demonstration that I made here today, when we looked at measuring the Bluetooth link itself and checking for audio glitches and dropouts. And the point I just want to reiterate, is the fact that we must use a system that has a true peak detector in order to reliably pick up even the smallest amplitude, shortest duration glitches. And we saw earlier that the various methods that we talked about, whether it's looking at an oscilloscope trace, listening to the signal, measuring its amplitude, measuring its RMS THD plus N, all of these methods potentially have their flaws, and it is the true peak oversampled and interpolated measurement function of, in this case, the D-Scope, that is the tool to use in conjunction with our unique event manager features, which allow you to automatically detect any limit breaches from, in this case, your THD plus N measurement. So finally then, we have used the D-Scope Series 3 audio tester measurement system quite extensively during today's demonstrations, and this system is quite unique in it is the world's first and only audio tester measurement platform that fully integrates testing tools for Bluetooth audio devices. We looked at the sound card I/O functionality, which allows us to directly address Bluetooth and other Windows audio devices connected to our host PC, and this importantly allows us to make real-time closed-loop measurements of Bluetooth and other Windows audio devices, negating the need for any external signal generation software or offline analysis of WAV files. So this is a very powerful feature that I hope we have illustrated to you here today. A few topics for further consideration. We've made several references to the fact that we just don't have time today to talk about everything in the kind of detail that you might want to understand in order to be able to fully analyse every component of your Bluetooth audio system. And one thing that I had no time at all to talk about was what you would do to make a microphone measurement. The theory is quite similar to loudspeaker measurements, but in this case you would typically use a full head and torso simulator with a mouth simulator coupled with a reference microphone in order to quantify the performance of your headset microphone. Windows audio device testing in the general context, we have already covered this in a previous Prism Sound webinar, so we'll make sure links are available to you so you can download this if you want to learn more about testing Windows audio devices in a general sense. For portable audio devices, maximum output levels are a very important consideration, and again this is something that we have covered in a previous Prism Sound webinar that you can download in your own time. Today we've been focusing on manual measurement methods which are appropriate for a research and development or verification testing application, but if you're working in high volume manufacturing environments then you want to be looking at automated measurement processes, and again this is something that we covered in a past Prism Sound webinar where we looked in detail at things like, for example, multi-tone testing. And then finally, we've got quite a comprehensive program of past webinars where we have covered electroacoustic design and measurement issues. All of these things can be accessed, downloaded and viewed in your own time from the following link, prismsound.com/webinars. And I'll ask my colleague Graham Boswell, who has been providing the support role here today, to just send that link through to you in the NetViewer chat area as a URL so that you can gain access to that immediately after today's event. I'd just like to say thank you all for your attention during today's webinar presentation. I hope you found the content useful and interesting. I'd like to say a big thank you to Howard Farah, who joined us from Cambridge Silicon Radio to present a good deal of the practical demonstrations here today. So thank you to Howard, and thank you to Graham Boswell, who was joining us in the support role on today's session. So we will collectively bid you farewell for now. We hope to see you on another Prism Sound Wednesday webinar in the not too distant future. Look out for updates from us when we'll be telling you about what we'll be discussing in future educational webinar sessions. But for now, thank you from all of us once again, and goodbye for now.